Last serious official talk of the program. It's a pleasure to have Connor close this more solemn part of the program. And in the afternoon, we have an informal talk by Nima, and then one more last coffee break, where I think there will be some music, I think. Right, Wellington? Yes. Very good. So there, it's really the final end. So yeah, Connor, please tell us about long-range Ising model.
All right, I'll start with a big thank you to the organizers, especially the local ones. It's been a wonderful workshop, at least for me. I'm sure it has been for you too, everyone who came out here. So thanks a lot. I'm going to talk about analytic and numerical Bootstrap results in that order for the long-range Ising model, which is something I worked on a number of years ago with Leonardo, Slava, and Bernardo, two of whom are in the audience. And it's a pleasure to return to it with Eduardo Laria, Maria Noki, and Filina van Vliet. And the most important thing to know about the long-range Ising model is that it is a non-local conformal field theory at the critical point. And that means that its conformal symmetry is not generated by a local operator of spin 2 at the unitarity bound. So because locality is a sacred principle, an important question is why on earth would you relax it and give it up? So one reason is that it allows you to have critical phenomena in one dimension where a lot of techniques simplify. And this has been known since at least the 60s. You can find papers that write down this Hamiltonian for the ferromagnetic long-range Ising model in one dimension. Where you sum over all nearest neighbors and interactions decay like a power law. And a more recent motivation is what I'm going to call SUSY-like features. And one of them you can already see, that there's this parameter S, a continuous parameter that has a critical point for every value of S. So this is a little bit like having a conformal manifold. But as we're going to see, there are also non-normalization theorems in non-local theories. So besides the lack of a stress tensor, there are other parts of the spectrum that can serve as a smoking gun for non-locality. These involve protected operators. And you can even sometimes pair up their conformal blocks in a known way into something that you might be tempted to call a superblock. Also, a non-local CFT is what you get if you take a defect CFT in D dimensions and then restrict to the defect that lives in P dimensions. This is related by a Weyl transformation to a subject we've heard a lot about in this workshop, which has become quite important in the last 10 years, QFT and ADS. And finally, if you aren't swayed by any of these reasons to study non-local CFTs and would prefer to just avoid them altogether, which is completely legitimate, the last point is that if you don't have a complicated system involving external stress tensors, then avoiding them is actually hard. There are a lot of numerical Bootstrap plots that have a large allowed region where people are working on shrinking it. And I think in the majority of cases, families of non-local CFTs can be used to explain why no island has been found yet. So if you're doing something numerically intensive, having some sense of what non-local CFTs are out there can be helpful for making sure you choose sensible gap assumptions from the beginning without wasting too much time. So let's start by writing down a continuum, a Landau-Ginzburg description for the long-range Ising model in the continuum limit. So just as Wilson and Fisher used a phi to the 4 interaction to deform a free theory, this will be a phi to the 4 deformation of a generalized free theory. So I'll start by writing the action of generalized free theory. And as expected, it will not be the integral of something local. It will have two integrals. And I'm also going to anticipate the role of defects by working in p dimensions. And I might as well generalize this lattice Hamiltonian to p dimensions as well by just writing this. So this is generalized free theory, and then adding the interaction looks like this. And just to hammer this point home a bit more, what is generalized free theory to somebody raised in the local world? Well, it is free theory in a higher number of dimensions, restricted to a p-dimensional trivial defect, where the number of bulk dimensions, the codimension, depends on the scaling dimension that you want this generalized free theory to have. So the UV dimension of this generalized free theory is p minus s over 2, as you can read off. And this means this is associated with a defect of codimension 2 minus s. So these are two descriptions of the long-range Ising model that have been known for a long time, but there is one more, because another action which no one stops you from writing down is this generalized free field of dimension p plus s over 2. So we can change s to minus s. And then instead of a polynomial interaction, you can couple it to the short-range Ising model, written schematically in this way, and then do something like this. So if you look at S1, phi to the 4 becomes marginal when s is equal to p over 2. So this will be a line of generalized free theories. And then going to the left, say,
So for the short-range Ising model is also in the p dimension.
yes. Oh, yes. So Xijin asked if this short-range Ising model that we're coupling to also lives in p dimensions, and it does. So if epsilon defined in this way is positive and small, then you can get a perturbative flow from this operator and reach this long-range Ising fixed point. So there's this line. And here you can take this decoupled system of the generalized free theory plus short-range Ising, and here, if this quantity is small, so p minus the short-range delta sigma, which I'm going to call delta sigma star, so this is just 1/8 in 2 dimensions, it's 0.518 in 3 dimensions, it's the familiar thing. If this quantity is small, then you can trigger a weakly coupled flow using sigma chi and get to a fixed point. And in this 2017 paper with Leonardo Slava and Bernardo, we conjectured that these two lines do not miss each other, they actually hit each other, meaning you have two descriptions of the same fixed point with complementary regimes of validity. So when Wilson and Fisher approximated the Ising model by deforming a theory which is solvable in 4 dimensions, the 4 minus epsilon expansion, people imagined that it should also be possible to describe this fixed point by deforming a theory which is solved in 2 dimensions and get some sort of 2 plus delta expansion. This problem has been open for 50 years, but the analogous problem in the long-range case has actually been solved. So because there are 2 descriptions, I can write down perturbative estimates of anomalous dimensions in 2 different ways, the epsilon expansion and the delta expansion. So let's start doing that a little bit. The first one to write down is very easy. The anomalous dimension of phi is 0. So
Just so I understand, this line being connected at this point of the talk, it's a conjecture, right? But you are going to explain why this is connected, or?
oh, it's a conjecture at the beginning of the talk, and it will still be a conjecture at the end of the talk.
Okay.
I'm going to use this, not prove it. Yeah. So this deforming operator is local, and that means that in the 2-point function of phi, if you got divergences, you'd only be able to renormalize them by giving a counter term to this local kinetic term, not the non-local one here. And this is an irrelevant operator, so it better be the case that these divergences are just absent to begin with. And this has been proven by mathematicians, I believe. But to see this in the physics way, you can compute the first few orders and start to convince yourself, but it's better to note that the higher dimensional bulk field is free, so this 2-point function will need to be harmonic. And this allows you to show that the scaling dimensions of the defect modes of this bulk field are fixed, and thereby prove this. Another one of the defect modes is phi cubed. So phi cubed will have an exact anomalous dimension as well, and it turns out to be epsilon. And you can also see this because theories of this form have non-local equations of motion. So you can just get the equation of motion in the usual way, and it no longer tells you that phi cubed is in the same multiplet as phi, like it does in the local Wilson-Fisher fixed point. It tells you that phi cubed is an independent primary, which nevertheless has a tightly constrained scaling dimension. And around the other side of the duality, it's the exact opposite. So now it's chi, which has a dimension that is 0 loops exact, and sigma, having a dimension which is 1 loop exact. And once again, you can get that using a non-local equation of motion or the defect point of view. Moving on to some non-protected operators. You can look at the leading twist, the double twist operator of leading twist and spin 2. So I hope it's clear what I mean by this notation. This is not a stress tensor anymore because this is a generalized free field, not a free field. This anomalous dimension looks like this. And already in the 70s, Fisher, Ma, and Nickel solved for the leading twist of spin 0. So this is just phi squared. And they got this formula. Just as an example. And then around the other side, we have complicated integrals in conformal perturbation theory. So we had to do them numerically, but we're pretty confident in the first few digits. So I'll write the analog of each one.
maybe it's stupid, but phi and chi, when they meet, they're going to become the same, right?
Phi cubed and chi are going to become the same. Sigma and phi will become the same. So that's why you have this behavior.
Can you say again? So phi cube from one, is what becomes chi on the other corner, and chi becomes, and the chi cube becomes phi? Okay, why is that true?
Yes, sigma becomes phi. So this phi being like the spin field in, yeah, phi is a spin field whether you're in the local case or the non-local case. So this has a protected scaling dimension. It's p minus s over 2, and then that means that p minus s over 2 is just delta sigma when this delta goes to 0. And this basic picture goes back to SAC. And some people have disputed it since then, but none very credibly, I would say. All right, so there isn't very much perturbative data in the literature that you can find for this model. This might be it. And we want to generate a larger data set. And this task splits into essentially 2 steps. There's the spinning operators and the scalar operators. For the scalar operators, we're going to make use of the defect point of view quite a bit. And for the spinning operators, we're going to use the Lorentzian inversion formula. And the Lorentzian inversion formula is convenient because it works at the level of a 4-point function, so you can use it to extract an infinite amount of CFT data at once.
T and I missed the annotation. What is T and epsilon here?
Right, so when you work with this coupling to a short-range Ising model, the short-range Ising model has a stress tensor and an epsilon energy operator. So
Okay, so T is the stress tensor, and okay, and the epsilon is energy. Thanks.
yeah, so in the long-range model, T is the would-be stress tensor. It recombines. So the first candidate for using the Lorentzian.
Okay, so the T operator is in the S2 series language, right? And in the S1, it corresponds to the 5502. Is that true, or?
Yes, yeah, so just
So
like,
shall they? So the T operator should have the same enormous dimension if they duality map, right? This is true. Is that true? Or?
yes, if you could compute it non-perturbatively, then they would, yeah, have the same dimension.
Okay. So from your perturbative result, are they close or?
You mean is the
Gamma
the
T
leading
and
order delta expansion a good approximation to the leading order epsilon expansion?
yeah, I mean you can just directly compare these 2 different expressions, right?
I guess. I wouldn't expect them to be particularly close.
Okay, thanks.
Sorry, Connor, did you perhaps privately just check whether this conjecture holds near d equals 4, where both flows are short?
This check was part of what SAC did a long time ago, and then this local kinetic term becomes weakly irrelevant, so that becomes important.
No, but SAC was not aware of this other picture.
That's true.
That's what I'm asking, whether if you do it in both ways, in that case, they should match. You have not checked?
We had a little bit of a check at large N, but I would like to do more in either case.
No, I should say that this conjecture is not as mysterious as it is, because look, if you look at the first description S1, in the limit where S is becoming larger and larger, so in fact this non-local Ising model, it's becoming kind of more and more local, because this interaction X minus Y is becoming more and more peaked at short short separations. So it's not a big kind of conjecture to say that, okay, at some point it's going to become so local that in fact it's going to become a short-range Ising model. And in fact, that's what people always believed. So the our contribution, I would say, was to realize that not only you are going to transition to this short-range Ising model, but you can actually do some reasonable perturbation theory around that point. So, and our latest simulations who indeed show that this transition happens in 3D and 2D.
Okay, so if we want to work with the Lorentzian inversion formula, one 4-point function that you might try using it on is the 4-point function of chi. So the operator that becomes a defect mode of the field in codimension 2 plus s. But here, all the non-trivial CFT data starts at 4 loops. So by symmetry, you have to insert sigma an even number of times. So 1 in 3 loops are going to vanish. But at 2 loops, the anomalous dimensions also vanish. And that's because when you only insert sigma twice, there's no way to tell the difference between sigma coming from the short-range Ising model and sigma coming from another generalized free field, whose dimension is just the shadow of the one for chi. And this coupling of 2 generalized free fields that was studied by Witten in the early days of ADS-CFT, this is an exactly marginal deformation. And not only does it give no anomalous dimension to the deforming operator, but it gives no anomalous dimension to any of the operators. So you would have to go to high order to study this one with the inversion formula, so we're not going to do that. We will instead study the 4-point function of the operator, which becomes a defect mode of the field in codimension 2 minus s. And for this function, we can write the conformal block expansion, but write it in a perturbative form. So there's a 0th order OPE coefficient squared, first order OPE coefficient squared, and so on, times the conformal block where you do the same thing. And then just by Taylor expanding, you get this. And there's a derivative here. And then I'll write one more term. And so on. And then what you use is the fact that conformal blocks go as u to the twist over 2. So if you differentiate this with respect to the dimension twice, then you get log of u squared. And this has a double discontinuity. But power laws and single logs do not have a double discontinuity. So the double discontinuity at 2 loops first comes from only 0 and 1 loop data, this lambda 0 and gamma 1. So you can use the previous order to fix the next order. And then optimistically, Simone's Lorentzian inversion formula will give you every piece of CFT data at 2 loops, which you can then use to fix the 3-loop double discontinuity and keep going. So in practice, degeneracy will eventually kill you, but this is still a relatively efficient way of reducing the amount of work in perturbative computations compared to Feynman diagrams. So just to see how this works, I'll write the Lorentzian inversion formula. It is this. And I'll write it in 2 dimensions so that conformal blocks factorize. So these k's are the 1D conformal blocks, just a power law times a hypergeometric function. And this function C of delta NL is the spectral density. So this is what you use to extract CFT data once you know the double discontinuity and evaluate this integral. So non-perturbatively, it looks like this. Yeah, just single poles. And then perturbatively, you should do the same thing that we did here. Take this residue and pole, expand both of them in epsilon, and then when the whole thing is expanded in epsilon, you get higher order poles, and you end up seeing that the double poles are associated with this data, the triple poles are associated with this data, and so on. So it's completely analogous. And again, we want to use this 1-loop data, which is non-degenerate, to fix the 2-loop double discontinuity and therefore get 2-loop data. And in the local Wissam-Fisher fixed point, this was done by Aldai, Henriksen, and Van Loon. And it was very nice at 1-loop because only the operator phi squared contributed. So in the free field OPE, phi cross phi, you have a single exchanged operator of each spin. So just the leading double twists. And you never have to act with box because box phi is 0 in the free field. Here for a generalized free theory, you do have to act with boxes. So in principle, you might be pessimistic about whether the same thing will work, but it does work. So this 1-loop data that serves as input the 1-loop anomalous dimension of this operator, it's epsilon over 3 for phi squared, and it is 0 for all of the other values of n and l. And it's actually very easy to prove this. So if you look at a double twist in position 1, a double twist in position 2, and then insert phi to the 4 at position 3, by Wick contractions, what you're going to find is 1 pairing with 3 twice, 2 pairing with 3 twice. And no matter what the sprinkling of derivatives is, hitting x1 and x2, some derivatives here, some derivatives there, all this can do is increase the degree of the singularity for x1 going to x3 or x2 going to x3. It will never increase the degree of the singularity as x1 goes to x2. So therefore, this power law, I believe it's 4n plus 2l, which you have to get just from the Polyakov form, you only can get if n and l are 0. So phi squared is the only double twist with a 1-loop anomalous dimension. Therefore, we know this bit. Therefore, we know the two-loop double discontinuity, and we can proceed to evaluate this formula and get the two-loop spectral density, and just write the result.
What exactly are we trying to do? To compute many anomalous dimensions to better check this duality? What exactly are we trying to do?
So we're computing many anomalous dimensions in order to compare to numerical bootstrap results.
Numerical bootstrap results, okay.
Yes. So yes, I'm not just going to present old numerical bootstrap results and say now we can match the perturbation theory a bit better. There's also going to be a new way of doing numerical bootstrap, and the kinks will be much sharper.
But still, this computation is perturbation around the top corner, right?
Yes.
And the numerical results will not be perturbation at all, right? They will be just exact.
That's right.
And so the idea will be you will do some Borel resummation or something, or you will just tune to a regime where you are close to the upper corner.
I'm going to vary parameters to explore both corners. And this is the spinning CFT data part of the talk, but once I talk about perturbative scalar CFT data, there we're going to have estimates around both corners. But yeah, the point I want to make about this two-loop spectral density is that it has a double pole at dimension L plus 1. So this is the leading double twist. But it does not have poles at dimension L plus 3 or L plus 5 or anything that would describe the higher twists. So this anomalous dimension, which we now know at two loops for all n and L, this is only non-zero when n is 0. And we know exactly what it is in that case. So we started, I'll just say we started with something that was different from a free theory because you didn't have this equation of motion, this shortening condition. But now we're seeing that it might not be as different as we think because these extra operators with boxes that are there, they actually don't renormalize at two loops.
So I have a question. So when you do the analytical bootstrap, you just study the four-point correlator of the Skinner operator, right? But in principle, how do you know the Skinner is from S1 series, not from S2 series? So how do you tell the difference between the two series of the Skinner?
Well, we can input perturbative data. So this has dimension p minus s over 2, and that means it's like p minus epsilon over 4. So that's part of the epsilon expansion.
Okay. Oh, so then if you input another one, then you can get the epsilon expansion of the chi?
Yes, exactly. So this one loop data that we started with would have to be two loop data. Mm-hmm. Okay, it would have to be ordered delta squared data, which is like 4 loops. So it's just technically harder, but indeed you can do that in principle.
Okay, thanks.
And maybe I will leave this on the board.
So the equations of motion of the bulk theory, if you interpret S1 as a defect, they gave you gamma phi equals 0, but if you apply them to, for instance, higher spin currents in the bulk, do you get some of these anomalous dimension being 0? Can you derive some of these results from that perspective?
So the defect perspective gives you a way of finding infinitely many odd spin operators that have no anomalous dimension, and these serve as obstructions to the conservation of higher spin currents. So the moment the defect theory becomes non-trivial, you expect everything in the bulk to break except the stress tensor, and that's reflected in the fact that these don't renormalize.
So are these the n equals 0 and all odd L part of these ones? Because the higher spin currents are phi, del phi, and they will break in the transverse direction, so there's generalized displacement, that's what you're saying. So are some of these anomalous dimensions going to be 0 at all orders?
They're not double twists. I believe they are quadruple twists because they have phi and phi cubed in this description. So it's a little tricky to precisely identify what they are in terms of phi. There's some degeneracy there.
It's the usual double twists instead. What happens to those?
Well, it must be that the bulk doesn't protect them.
Yeah, which isn't it strange? So anyway, you're positive that this, if I keep n equals 0 and I increase L at 2 loops, I get anomalous dimensions. This is something you're gonna say.
Yes.
Okay, thanks.
Does this result also follow from those locality conditions if you plug in the double traces as that O?
Yes, so
You can show this result from that.
Yes, that is one way to derive these things as well. You can, yeah, you can start with some easy computation of OPE coefficients and then use it to derive.
It's a direct consequence of the equation of motion, indeed.
Okay, yeah, that's a way to think about it. Right, so the inversion formula is one method for gaining an order of perturbation theory, starting with something at 1 loop and getting out something at 2 loops. There is another method that was very useful to gain an order of perturbation theory for us, and it's in some sense already written on the board, but I want to explain it. So if you have a free field in the bulk, so I've already said that it's harmonic, and in particular, what Laplace's equation buys you is that the defect OPE of this field, as you take the perpendicular x to 0, for every transverse spin, so every spin under SOQ, which, okay, I'll confusingly call it S here. No, what's a better letter? Capital sigma. Okay. For every transverse spin, there has to be exactly 2 fields, 2 operators in this defect OPE. So you can work all of this out just from Laplace's equation. Okay. So
I'm sorry, why do you have to complicate your life like this? I mean, at the end of the day, you're just interested in the S wave with respect to these transverse directions, right? I think this is just a gadget to avoid.
Spin 0?
You could have just defined a free scalar field in ADS P + 1 with an arbitrary mass term, and you would have got exactly this Lagrangian. So
Okay, yeah. Part of why I'm discussing this is just because, as a tangent, there's some nice work that's involved this, and I want to mention it.
there's some nice work related to taking into account these modes.
Yes. So this is part of a classification of defects of conformal defects for the free field. Due to yeah. Ado, the other Pedro, Balt, and Chung. So anyway, for every transfer spin, there are only two operators, the plus and minus modes, and they have scaling dimensions given by this. And the trivial defect only has the plus mode, doesn't have any minus modes. And with a little more work, you can show the converse. If you don't have any minus modes, then the theory you have must be a trivial defect. And having a minus mode is actually not so easy, because if you make Q large enough, or if you make this transverse spin large enough, then you will violate unitarity. So this paper I mentioned, the authors have a nice table for all the integer values of P and Q, where they show all the cases that allow conformal defects for a single bulk free field to exist. The list is fairly restrictive. And considering the long-range Ising model, you can think of that as an extension of the table by considering fractional codimension. So to take their bulk two-point functions that exist for those special integer values of P and Q and analytically continue to fractional Q, what you can write down is this two-point function where all of the transverse spin greater than 0 part is just a trivial dependence. So for transverse spin greater than 0, you have indeed only a plus mode. So this is trivial. And then the correction at transverse spin of 0, where it will look like B plus for spin 0, so I just won't write 0. This 2 is squared, not transverse spin 2. And then you have B minus squared over this. And this is the defect channel expansion of the two-point function, which we often write in this way. Now there's a crossing equation which sets that equal to the bulk channel expansion. So on the left-hand side, this side involves the defect OBE coefficients B. And on the right-hand side, you have a bulk 3-point coefficient, which is known from free theory, times a bulk 1-point coefficient, which is an unknown parameter. And you can solve this defect bootstrap equation and relate the b's to the 1-point function of phi squared, and you end up getting this solution. So B plus and B minus are both determined once you know the 1-point function of phi squared. So this is a very standard computation. Something that's a little less standard but very powerful is when you add one more operator to the game, which is on the defect. So you add a generic operator here. Now the left-hand side is going to involve the b's, but also 3-point functions on the defect, whereas the right-hand side is actually going to be 0. Because once you bring these bulk points close together, you'll get some highly non-generic operator in a free theory, which will most likely not have this generic defect operator in its bulk to defect expansion. So you have to get 0 on this side. And that means this expression with the defect 3-point couplings and the B plus and B minus coefficients ends up giving you a constraint. Yes, so Pedro is wondering why, why the right-hand side of this equation is 0 for a defect operator of generic dimension. And that's because in the bulk, the fusion of these free fields has to give you phi squared or phi squared with 2 derivatives or phi squared with 4 derivatives, just some known double twist. And when you take the bulk to defect expansion of that double twist, the equation in motion limits the number of modes that can appear, so you won't be able to get something that has a completely generic scaling dimension here.
What if the data is not generic?
Right, so the relations that I'm going to talk about and that are over there have degeneracies when this scaling dimension approaches some double twist value.
So that means the 3-point collider is not always there, right?
Yeah, so this is not always 0, but it's non-zero in sort of boring cases that we can account for.
Okay.
So previously, when I wrote these anomalous dimensions that I just erased, phi, phi cubed, sigma, and chi, if you were quick, you would have noticed that they were shadows of each other. So phi and phi cubed, their dimensions add up to p. Sigma and chi, their dimensions add up to p. And this is not just a coincidence of scaling dimensions. Really, this non-local equation of motion I talked about, which protects the scaling dimensions, literally is a shadow transformation. So you can use it in 3-point functions and take a 3-point function involving phi and turn it into a 3-point function involving phi cubed. And you find that these are proportional, where the proportionality involves gamma functions. So the arguments of the gamma functions depend on delta sigma and delta chi, for example. But delta and sigma and delta chi have dimensions that are fixed in terms of p and s, and that means they're fixed in terms of p and q. So all I've done here is written the defect dimension and codimension in the gamma function. But there are also these annoying normalizations of phi and phi cubed, because the fields that appear in the action that are used to derive the equations of motion, they can have some non-trivial relation which changes along the flow to the unit normalized operators at the IR fixed point. So we need to have these factors here. But using this defect crossing equation leads to a bit more of an insight about these normalization factors. So I'll replace them with expressions in terms of B plus and B minus. Which one? Yeah. In fact, B phi cubed and B phi. And here it's just the inverse. And again, B phi cubed and B phi are solved in terms of the 1-point function of A squared, or the 1-point function of phi squared. So now we can get some mileage out of these relations perturbatively, as Miguel was suggesting. So taking these three operators, for example, and unit normalizing them and computing an OPE coefficient, just in generalized free theory, you get root 2. Two more. And knowing the left-hand side to 0 loops tells you stuff about the right-hand side to 1 loop. So this tells you that the anomalous dimension of phi squared is epsilon over 3 at 1 loop. And then we can also use this to solve for a phi squared perturbatively. So we get what a phi squared is to order epsilon squared, just from this generalized free theory data on the left-hand side. And it's a bit of work, but this epsilon squared coefficient, we've checked it in the traditional way using Feynman diagrams. So this is a simpler way of getting the same thing.
So, sorry, maybe can I just make a comment? I mean, the way that you derived it, these relations appear a bit mysterious or, I mean, very specific to this particular model. I should just comment that all these relations and this normalization theory and so on, these are basically these locality constraints that Nat and also Marco mentioned in their talk apply to the specific case where you have this free field in the bulk. So there,
Yes.
all these relations follow. So.
Yeah, so you can definitely get this from the approach in Nat and Miguel's paper. I just want to mention that this defect crossing equation I used actually does hold, again, in all defects for the free field. So for the non-local equation of motion, you might complain that that's something particular to the long-range Ising model, but we also have a derivation that of the fact that these relations are more general. No, this is non-perturbative. So once we do this, we can go to the next order.
So it must be something silly, but I'm just confused. So if I insert an operator, typically, unless there is some symmetry, it has overlap with everything. So why wouldn't it have overlap with phi-phi? There's something very...
It's because these fields exchanged in the bulk are leading to it, so they're currents. I think that's the statement.
Because they're...
A conserved current of a free field has to have only particular defect modes, only particular things you can overlap with.
So if you remove the bottom field, those top fields, they produce everything that they could on the defect, right? You can do a bulk to boundary OPE and they are free. Why are they free? I think that's probably what I'm missing. Aren't we doing an interacting theory? Why are things free?
The interaction is localized to the defect, so it'll change the defect data, but not the bulk data. So, like it would be weird if some generic operator just suddenly appeared in the defect OPE of.
Sorry, I'm also a bit confused, so I'll ask again. So the currents, the double twist operators in the bulk, they have conservations equations, and so as long as you consider scale, I guess delta is a scalar, right? The one on the boundary? Or,
it doesn't have to be.
Well, at least it's very clear if it's not a seed, so that it's not going to be automatically conserved, so it won't overlap. But what about phi squared? The scalar phi squared in the bulk, the overlap with the generic operator delta, what's the argument there for it to vanish? From equations of motions, it doesn't seem totally obvious because you're applying them to phi square, which normally allows for more things.
Yeah, so phi squared in the bulk, why does a generic operator here not appear in its
Exactly.
defect OPE?
I mean, I probably should know, but just I don't see it at the moment.
Yeah, I've sort of seen this thing for too long that I stopped questioning it. Yeah, there definitely should be a good way to explain it that hopefully will an understanding that hopefully we'll come to by chatting somewhere after this. But yeah, once we've done this computation, of the left-hand side at 0th order, we can do it at first order. So these anomalous dimensions at first order, these OPE coefficients, you can still get them. How much time?
Maybe 5 minutes.
Oh, okay, yeah, I will. I'll just write one of these. So you can compute this. And this gives you a new proof of Fisherman-Nichols anomalous dimension of phi squared, and it tells you this next term in a phi squared. And then a phi squared around the other side. You can do this exact same thing around the other side of the duality. And therefore get some thing that you can overlay on a plot. So here's where the plotting is going to start. So this expression involving epsilon and delta for a phi squared. We also have an expression involving epsilon and delta for this leading spin 0 unprotected operator. So phi squared or epsilon. We can use these expansions from either side to make some sort of Pade approximant and have a plot where we overlay numerical bootstrap data. And for the numerical bootstrap, the plot is being done as a function of a phi squared. So that means we're using these relations for every exchanged operator in the continuum, which depend on a phi squared. And if you set the dimension and codimension so that you're close to the generalized free theory end, then you end up getting this very sharp kink, which exactly touches this line. And then when you move a little bit more away from the generalized free theory end, you see that you're getting a kink in the right place, but also a kink a little bit above it. And then the distance between these two kinks becomes wider and wider, but there's always one that nicely tracks the perturbative prediction from the long-range Ising model. So we believe that we've found it numerically, at least in 2 dimensions. And 2 dimensions was the harder case. So there's a bit of history, but if you take this old plot in 2 dimensions where there's a kink at the short-range Ising model and then a bunch of higher minimal models on the boundary, and then the long-range Ising model lives inside the allowed region. It's a well-known fact that if you go to a larger system of correlators, 3 correlators involving sigma and epsilon, this upper bound does not change. You still get the exact same thing, even if you say that sigma and epsilon are the only relevant operators, which is a condition that should naively rule out the long-range Ising model. So if something more restrictive, if only 2 relevant operators is still not enough to get you anywhere near the long-range Ising model in this 2D plot, then adding in this 3rd relevant operator, even if it's highly constrained by these locality conditions, will still not give it to you. And yet in 2 dimensions we are getting kinks at the long-range Ising model, and that's because we're not plotting one scaling dimension in terms of the other, we're plotting one scaling dimension in terms of a different parameter. So this is a lesson that looking at different parameters can often be very useful, even if you don't increase the numerical complexity of what you're doing. One example maybe I should mention is a paper by Nathan, Shai, and Silviu called the M-theory archipelago, where they did some n=8 3D superconformal bootstrap where the state of that is still far from the point where you can get islands in the space of scaling dimensions of long operators, but you can get islands if you plot OPE coefficients in terms of each other. So I want to say there's a morally similar thing that's happening here. And
What are the different curves?
Yes, so changing P or no, it's changing Q or changing the value of S. So P is always 2. We're looking at the 2D long-range icing model. But yeah, different delta phi. I should write what they are, the ones we've done. So 0.425, 0.35, 0.275. And then there is one more that I want to discuss, which is at 0.2. And by the way, this kink, so we have a plot of a phi squared versus delta 0, the leading spin 0 unprotected operator. But delta 2 is also something that was quite important. I showed some results for it. And extracting the spin 2 operator dimension, the spin 2 gap, can be done in many different ways. So one thing you can do is go to this point in the numerics and then just bound the gap for spin 2. Another thing you can do is go to this point and then use the extremal functional method to get the spin 2 dimension as well as several other dimensions. And finally, what you can do is make this plot on the gap, on the spin 0 gap, but impose different spin 2 gaps along the way, and what you get is kind of nice. This kink on the right moves inwards, but the kink on the left does not. The kink on the left that we trust the most is stable, and that gives us further confidence that it's describing a real model.
Does that mean the kink on the right is the stress tensor?
All the way on the right, yes. Yeah, it would be nice to find some perturbative description of what this might be. We haven't found one yet. And the last thing that gives us a lot of confidence is that this value of delta phi equals 0.2 has been studied by 2 different Monte Carlo groups. And they had a bit of a tension in their results. So there are some error bars here, which can be found in a paper by Marco Picco in 2014. And then there's another paper with error bars here, which nicely capture the location of the kink that we found. And this paper uses a different lattice model, which is argued to be in the same universality class as long-range icing, but is better at accounting for finite size effects. And it blames the discrepancy on finite size effects. So this is a paper also in 2014 by 3 people. And I think something that would be nice for the future, besides doing this in 3 dimensions as well, is adding more correlators and or more gap assumptions in order to maybe get an island here which fully kills this old Monte Carlo result. So this is a status report. We're still doing some of these things, but thank you for your attention.
So just a very naive question about the motivation part. You mentioned that these theories are hard to avoid when you're trying to study a short-range model. But if I just put the stress tensor to be conserved and put a gap above it, don't you expect them to be excluded? Or they're not sensitive to this?
If you have a continuum of spin 2 operators, there's no way to guarantee that the isolated spin 2 operator below it is part of the spectrum. If you put enough of a gap, though, then I agree.
So I put the stress tensor to be conserved, and you're saying I need to put a big enough gap for them to...
Yeah.
Okay.
That's true. Oh, yes. So Miguel said that you can maximize the OPE coefficient of the isolated stress tensor to force it to be there. This isn't done all that often, I don't think.
Okay, I have a question about the serial of S2. So if you think about the equation motion of the operator sigma, then it tells us that the box sigma should be equal to sigma cubic and plus chi. That means the mixing of chi and sigma cubic is a descendant of the operator sigma.
Okay, you might have to slow down because the equation of motion
Of sigma.
I'm familiar with has a box acting on chi, or like a.
Sorry, yeah. I mean, if you think about the equation motion of operator sigma.
How do you get that from this abstract CFT?
I mean, you said that's a local IC model, right? Is that true?
Yes.
So then we know how to write down its equation motion, right?
It has null states in
It's
2D, but
I mean, it's like Lagrangian is like for the local.
this is not a Landau-Ginzburg action for sigma. This is really the theory, the short-range Ising model at the fixed point.
Okay.
Any other questions? So if not, I would love to thank Pedro and Francesco, who truly did all the work in the organization. It was an amazing amount of work, and I think this has been a flawless organization. It's one of the best venues we've ever been, and you have been amazing. Thank you very much.